Hi everybody. Today I'm going to talk to you a little bit about Lagrange multipliers and slack variables. So I have slack variables pulled up here. So in our overall scope of work, today we're trying to use the Broyden method to minimize and find zeros in a function. However, we have an inequality constraint in a 2D Rosenbrock function. That inequality constraint is x0 squared plus x1. It has to be less than or equal to 1. So I'll write that out for us. So I'll put it under 1. Let's get a fat. And we'll say that x0 squared plus x1 must be less than or equal to 1. So that's kind of our end function constraint that we want to apply. So in our world today, we want to use the slack variable, which is a way of transforming a function as an inequality to an equality. Using these, we can create a very specific solution. So we're looking at the second bullet point, which is slack variable is positive at a particular candidate solution. There's a constraint not binding there. So essentially, we're going to try to be using these slack variables to create a function with an inequality. Whereas with the Lagrange multipliers, the biggest challenge is to find the local min and max of a function. So when we use this min max, we can also create these Lagrange these Lagrange multipliers. We can find the min max, and from the min max we can find slack variables that are suitable for our function, which end up creating a lot more in-depth analysis as to what we can do with the Broyden method, using the Sherman-Morrison formula and solving the 2D Rosenbrock function. So now that we've kind of talked a little bit about the theory, I'm going to jump in and start going through the code and kind of understanding a little bit more as to like the visuals as to what we're doing here. So I'm going to go into our code. Don't worry if you haven't seen this code before, you can always look at my previous video, and we coded all the way through this to get through the first set of the Broyden, and so scroll through. So this is our Broyden method without Sherman-Morrison, and then to recalculate using the Sherman-Morrison formula, which is this UV and then J inverse, or Jacobian inverse, which, if we go back to our OneNote, you can see that this the J inverse equals the J inverse plus and then the transform of the function, which helps us solve the Broyden method a lot faster without as much iterative guessing. So now to kind of get into how we're going to take this Broyden function and make it solve a little bit more complicated of a problem. So to do that, we're going to define some variables. So our pring equals, we're going to put in, let's just make this a random number generator. So our P, random number, P, RNG is a random number generator. So we need a pring key, pring key, and that's going to be 1, 2, 3, 4. Make it easy, easy, easy. Now we need to define our Jacobian, which let's define it as Jax. We want a random uniform PRNG 3 by 3. Now we need to define our function. F equals another Jax dot random dot uniform, and we need our pring, and the shape for this one is going to be more 3-1. F, now we need our FP. In essence, we're defining all of the variables that we had previously defined through through calculations, instead of creating these random uniform matrices. So before, as you can see, our Jacobian F, FP were all defined through functions and callouts. So now that we're doing these callouts, we will find our function looks a little bit different. We want J and P for our Jack's numpy. We'll then solve. And to solve this, we need J and negative F. Ooh. Okay, now we've defined all of our variables. Now let's define a function. This function is, let's just call it this is going to be our constraint function. So let's just define that. We're going to use a command called reshape to get our array into a 3x3, and we're going to return a squeeze. So we're going to take everything that we got and put it all together. JP at dx. So now that we got all that together, we're going to go all the way down here. We're going to set up our nonlinear constraint, or NLC. So now we're going to use the nonlinear constraint command. I'm not quite used to using this one, so that's our constraint, our variable name, our defined function, and then we're going to do a little J and P squeeze. Squeeze. Whew. Typing is hard today, gotta tell you. As things kind of go on and get more and more busy with things, it's kind of hard to focus on what's going on right here and now. But such is life sometimes. I apologize for low energy today. It's been quite a time. Okay, so now we have our nonlinear constraint using the nonlinear constraint command, and we're going to be subject to these inputs, and now we get to define another function that we want to solve on x, and we want the JP reshape. X reshape. Sometimes I remember to do the command, or let the code type so I don't mess anything up, but I don't always remember to do that. So we want to solve. We don't want to solve, we want a norm. We want a norm. Okay, so now we've defined, odd. Just kind of cutting in and out of my internet. What are you gonna do? What are you gonna do? Okay, we want our result to equal a minimize command of our function. So we're going to kind of force things through on our Lagrange multipliers and pretty much just all the stuff we've been talking about up till now. And to do this, we want a very specific method of minimization. That's this SLSQP. And we need to define our Jacobian. So our Jac equals Jax dot Jacobian of our function, which the Jacobian is kind of a replacement for our derivative. Sorry, pinched myself on my computer. And our constraints, well, are very simple nonlinear constraints that we already set up. So that's going to be our result. Now let's talk about, let's find out what we want. So we want res.x.reshape into a 3x3. Get out of 2, and then this is kind of our, so this method is actually called constrained minimization as our this is kind of the old, or that's the old-fashioned way of kind of doing this kind of stuff. So using our other way, so that it's kind of a back and forth against what the Broyden method and a more traditional constrained minimization. So now we have our Jacobian, or sorry, not our Jacobian. This is the Broyden update method, aka Broyden plus Broyden plus the Sherman-Morrison method. JMP dot norm of dx. And this is our Broyden update method. So that's our, from above, that'll be this block of code, that's our Broyden update method, whereas the next one's a constrained minimization, which is a more traditional way of having solved this. And we ended up with a two pretty different answers as to our actual minimization, but that actually shouldn't be what it is. They should be the same. Well, I think I figured out what was wrong. Whoa, I need to learn how to type formulas. If I remember, or if you see V up here, or sorry, V up in the area has a squared value for the Broyden update method. Yeah, mistyped that one, and boom, there we go. Same answers across the board. So now we have this constrained method and our Broyden update method, which more involves the second. So we have the second and the third block here. And now that we've kind of created our two-form minimization, now let's focus a little bit more on accommodating on bounds around variables, so we can kind of more accurately define our limits and eventually apply our Lagrange multipliers and slack variables to get Lagrange multipliers for the min-max and slack variables to turn our inequalities. So let's go in and we're going to define our Broyden again, except going to give it a slightly different name. Since we're defining it again, we should probably name it 2. And now let's put everything together. I'm redefining all our variables. I'm hoping that they're pretty similar. And let's go in here. Let's grab these so we don't have to type a bunch of times. relatively the same stuff. We don't. The extra additional things that we didn't define before is our x-min and x-max. So our x-max we are going to put at infinity, and for our min we're going to put at negative infinity, as a lot of problems end up having this infinite and non-infinite, or infinite and negative infinite numbers. Kind of helps us focus a little bit more on our local min-max or local minima and maxima instead of larger, more definable min-max. So, sorry, just checking out to see what happened. Why we're so different. Okay, I don't understand what the problem is. Line difference, I'm gonna move, save my changes. Ooh, no, I can get back to work. Okay. Now that our Google Colab, sorry, my internet's also been acting up, so we might see a couple of those incidents. It's good information, or it's a good learning experience too, because now you can see if you ever have a save error, you can just go in and accept your saves. So our JF, we need to find our Jacobian. And we want it for our function value, which if we don't have a Jacobian, then we want to just use the regular or we just want to use the letter J. Next. So our Jacobian equals JF as a function of x. So our Jacobian is a function of x. So now we need our J inverse, which is important for our Sherman-Morrison, or the overall Broyden method using the Sherman-Morrison method. It's we discussed that, like I said, in the past couple videos, and a little bit at the beginning of this one. So let's kind of create our function values. Equals function of x. So now that we've created all of our function values, let's create our iterable calculation. So max iteration. So for our max iterations, we want to look at some of the more important functions here. So we have this dx equals negative, j invert, woohoo, j inverse at f. And now we need to define some limits. So let's just call these alpha for our first max limits and min limits. This will be the min function, and we're going to define where it is. Can't say I've ever used the jack_snumpy.where function before, but besides learning how to perform all of this code, So we're defining our arguments for the x-where. Divided by function of dx. Okay. Now let's do that again for alpha min limits. Underscore min underscore limits. Equals our jmp dot min It's just kind of, I'm just going to kind of copy what we have above, except we're going to change a couple wordings. We don't want this at where x is greater than, or x is greater than x max. We want it at the minimum. So we have this minimum of the max and min. I also need to flip the signs because we can't be, or we're going to be greater than it all the time. Hopefully we're greater than the min all the time. And we now want our alpha value. So alpha max limits, comma alpha min. Okay, there we go. Now we got our alpha value. Well, now we got to figure out what we want and how we're going to run some calculations. So the first thing we're going to do is we're going to print out our alpha values so we know what we're looking at every time. Now we need to define some more variables, so our dx. This will help us set up something similar to our Broyden method. So we need to make sure everything's being updated. XP. Function of XP. Function is a function of experience. Okay. Now we need. Gotta make sure all of our iterations in and subject to the same lines as before. So for verbose, we want print xf if our Lineage norm, JMP Lineage norm of f of p is pretty much zero. And we want to break it. We don't want it anymore. And time to, now we need to apply the Sherman-Morrison method, which should look the same. Excuse me, should look the same as up here. So all over Sherman-Morrison. See. There we go. There's our Sherman-Morrison method, and well, what do we want? We want to return x and f. At the end, there we go. Nope, do not want 4. Just want x and f. Woohoo! Alright. Now we're going to define our second function since we didn't get any errors. It's just, I think it's pretty amazing. So our second function, well, what do we want? We want to return our original values from before. So our function 2, if we go all the way up to our function 1, all the way back here, we'll notice that we want this JX_NumB array as the sign values, and then we're going to plug this in right here, and then whoop. And now time to apply all of our methods that we've been learning. And this will be And here we go. Oh. So, something in our code isn't working, and we cannot find... it's a reshape issue. So let's kind of look through and see if we can find where our shape gets broken. Well, we don't want the original function value, we want our second function. That'll give us a better... There we go. Interesting. We got some values. I personally did not expect that. So our first Broyden method, still valuable. We weren't able to quite break it with all of our with all of our fun math. So let's check out what our second Broyden method will do. Broyden 2 with the same kind of iterations that we did before. So function 2, 1.95. And let's just kind of keep running this. We need to set a minimum for this, as we've defined them in the, or we haven't defined them in the function, but they are required to run. So let's define our minimum, which is our negative infinity. And now we need a maximum. X max equals of 1.0 or 1. And p positive infinity. So we're pretty much setting up what amounts to almost limits of a goodness gracious, a limit. We're setting up a limit. We want to figure out the weaknesses of this function, so we're going to set up a limit to try to define where we can hit our maximum and minimum. And as we do this, we can kind of continue on our quest to find how to mess with the Rosenbrock function, the 2D Rosenbrock function, to create more accurate minimums, especially with inequality. Okay, so now that we have our Broyden functions, we've set them up to work. We're actually going to try to decrease our increases in step. So to do this, we're going to define yet another Broyden function, which will be fairly similar to what we've defined before, with a very short exception. Yeah, so we'll start typing away, and I'll give it a pause because this is a lot of iterative programming that we've done before and explained before. So I'll get to where things are new, and then we can start talking about exactly why these are new, why we're doing the way we're doing it, and kind of the applications of the math principles. So I'm going to pause here, give you a chance to kind of wrap your head around what's going on, as well as maybe get to see some of or understand a little bit more of the Broyden 1 and 2. So, thanks. Alright, so we're back, and so our Jacobi, or Broyden Method 3, kind of set up pretty much the same, where we're defining our alpha, min, max, and now alpha. So to kind of help us better define and get a more accurate calculation, we're going to use a while loop. While, and then we want alpha to be greater than 0.01. So while this thing is going on, we want to try new dx's, and we want that to be alpha times dx, or xp equals dx underscore try. So we want to, increment our x's, and wow, didn't put an enter in. Whoops. Okay, now we want to define a couple more functions. So fp equals a function of xp, and then we want to create a norm value, which equals rjnp ln alg dot norm of fp minus, run too fast for my brain, fp jnp dot ln alg dot norm of f. So we want the previous iteration and the current iteration. So to kind of help constrain and make sure we're not running too far off into the wind, we set a verbose limit, and to do that, if we succeed at our verbose limit, we're going to print an f string. So that f string, you'll notice it's the same thing done above. The print the f string, we need an iteration of I, and dx is dx. So the curly Q brackets mean when you're printing an f string, I want the left of it's the string, the I, well in this case, and everything in the curly Q brackets is the actual values, so we want real numbers. So curly Q bracket, or alpha, curly Q brackets, we want alpha, surprisingly enough. And for our d norm, we want, can you guess it? D norm. And dx try underscore try is going to be our dx underscore try. A lot of pretty easy to figure out naming conventions here. Whoa. Gotta remember which side of the curly Q bracket we're running. Okay, so f equals f, and at the end we want to look at f equals fp2, or well, fp2. fp also. Right here. Okay, so now that we've defined all our prints, we want to look at things we're also interested in constraining d norm, that to be greater than 0, sorry. Keep pinching my hair, or pinching my arm on my computer. So if d norm is greater than 0, then we want alpha asterisk equals 0.5. Okay. If everything else in that isn't working, then we just want to break it. No more code. Now to set it up as well, or to set it up concurrent to the while loop, we want to set up another if function. So if our alpha is less than or equal to 0.01, then we want to look at our verbose constraint. If our verbose is greater than 0, Then we're going to print. We want to tell ourselves to reevaluate the Jacobian, because we don't have a good J there. Alright. Now, to continue writing our functions, so we have this J inverse equals the J NP dot. So we want the inverse. Well, that's not how you do in algebra. There we go. We want the inverse of J is over JF of X. And once we're done with that, we want the code to continue. Now to continue defining some more variables, so we want to kind of more fit into our Broyden method, let's redefine dx as the dx try. So whenever this ends up working out, we can get our real values. So this is kind of a lot of the same stuff we've done before, looking at the verbose constraint, printing the xf if it's greater than 0, and now we want to look at the j, or the norm. So if our norm is greater, or well, less than about our 1.0 e to the negative 12, so if, sorry I lost my place. Excuse me. The knowledge.norm of our function f of p is greater than, or sorry, less than 1 e to the negative 12. Then we want to break. We don't want it anymore. Okay. Now to paste in our Sherman-Morrison method from before so we can get a more accurate, and once we're done, we're going to return kind of pretty much we'll be looking at the same stuff we were for our other two Broyden methods. So let's get rid of this and paste it in. So now that we have our Sherman-Morrison method again, no breaks. Okay, so let's try out our Broyden 3 method. So we want this to be function 2 and 0.5 times GMP dot ones. We want 2 ones. We want verbose to equal 1. We only want to look at this, try its thing 20 times. And we need to set our min-max values, so our x min equals the array of negative infinity to 0.1 plus our EPS from before. Now that we've defined that, we need to define our Xmax too. So our Xmax is the JNP array. Pretty much the left side of our stuff. 1 point is EPS. And then positive infinity. So we want the left side and the right side. Okay. Woo! Let's run it. Whoa, local variable x. reference before assignment. Huh. Where do we do that? Where did we define x row? Let's see. We need 5 of Broyden 3, so J f is a function of x used before defining. I think we just need to reset our runtime here. So runtime factory reset runtime. Yes. Okay. Now runtime run all. See what we get? Oh no. Still running into an error. Huh. Let's kind of push on, seeing as that our third Broyden method kind of has some issues. We're just going to kind of push on and look at our equality constraints primarily. These equality constraints are for our larger Rosenbrock function. So, new line of code. So let's just look at this as the one equality constraint. Equality constraint. Type is hard. Okay, so we want to define our Rosenbrock function. It's a function of x. We want to return So for those of you who haven't seen it, this is kind of the Rosenbrock function that I was talking about in my previous videos. So we want, no, we don't want 22. We don't want to multiply by 22. We want to square it. And then we're going to square the whole thing too. And this is going to be plus another irritable value. So x at position 0. All squared. Okay, now to define our, so we've defined our Rosenbrock function, let's define our constraint. CNSTR. As a function of x, we want to return our inequality constraint, which is 2 times our x 0 plus x at position 1 minus 1. And we need to define our gradients. The gradients are partial derivatives of many functions. So you can also look at it in the form of physics. Physics uses a lot of gradients to define the function of, I want to say, electric potential uses a lot of gradients. So to kind of help us visualize this, the change of even pressure uses gradients. So with anything that holds more potential to go to another, if you wanted to calculate kind of how that system will try to equalize or equilibrate, then you want to use kind of a gradient or partial derivative of how they're similar, and using that you can find the function of transfer, or the transfer function, as to the equilibrating of these two systems. So let's, as we define our gradients, we will create a gradient of the Rosen function, and x2. Yeah, this. Excuse me. x2 times our Jack's gradient of our constraint, CONSTR, and our x as a x2 colon 2 here. Now that we're done with that, we're going to do a JIT, not to be confused with a GIT. We're going to do Jack's JIT, Jack's.JIT, and I'm going to define some equations. We want to, we're going to use the good old JNP.concatenate. And we're going to concatenate grads. It's quite the $5 word there. Concatenate grads and JNP dot at least 1D. Don't think I've ever seen that before as a function command. Seems like it'd be pretty useful. So now we have our return function, and we need to set initial values. So our x initial, or x naught, or x0, whatever you want to call it, is going to be JNP array. Since we had, or all of our functions have been sets of 3. Wow. We need to set our function, or 3 set values as our x naught, and now we need to perform the Broyden 3 of EQS, comma x naught. Local variable x referenced before assignment. So I'm missing something here. So x is defined down here when I should be defining it in the definition of Broyden. My question is, did I miss defining it in Broyden? Yes, because I suck at typing. Yep. That should resolve our issue from before. Gives us a bunch of iterable values, and that we should need, or that all of what we need to do is to reevaluate our Jacobian for that one. So let's put this in Broyden 3, and we get some numbers. Now we have our local min-max and the results of our Broyden 3 method. So let's kind of want to check, because it seems like the stuff's running, but it's always telling us to reevaluate J, and that looks right. Looks like we really do need to reevaluate our Jacobian. So now that we've completed our Broyden method with an inequality constraint, let's one equality constraint, my bad. We're going to look at it and try to put in some Lagrange multipliers to turn this into, I'm sorry, not Lagrange multipliers, that's what we were doing up here. This equality constraint is using Lagrange multipliers to create a reasonable equality function. Now we're going to go to the inequality and use slack variables. So let's, now that we've kind of completed our one equality constraint, we're going to work a little bit more to help kind of transform. Take a drink of water real quick. There we go. So now we're going to try to define another function and try to create a little bit more reasonable variables and make sure that everything we have works. So L, this is going to be our Lagrange multiplier equation. Now we want to return some of the stuff, or some of the things we've defined before, like the Rosenbrock function. And this is kind of our this is kind of how we were going to abuse our Rosenbrock function by using the Lagrange multipliers. So we also want to define a change in L equals x.jit command again, and we want it to apply to a gradient at L. Now that we're done with that, let's go x0, we need to define it, equals a JMP array, so we're just going to make x0 equal the same thing, which is nice. Make it equal the same thing, and we're going to redo the Broyden method that we've defined before, DL and x0. Now, using the Lagrange multipliers, we should end up with pretty much the same answers. Yeah, we did. Looks like we're a little bit more accurate when it came to that second device array. But we do have relatively similar answers in the first. It's just our second device array is a little different. So now that we've defined our equality constraint with the Lagrange multipliers, we're now going to use an inequality constraint to run the slack and define slack variables. So a lot of this inequality constraint stuff's pretty similar. We just have to go in and change some stuff. Actually, it looks like we are looking at pretty similar results with the inequality function. So let's go in. So we have one inequality constraint, which is good. Now we're going to go through and we're pretty much going to use the same path that we used for the equality constraint, except we will change some stuff because we need to set up an inequality, not this really easy to solve equality function. So we're going to adjust our variables here. So our device array starts a little larger. So our x0 is a JMP array, and our x and f are going to be now we're going to set this up so it has some max iterations, so we're not running off to the wind, except we're going to have a lot of iterations. So set this up. So we can kind of understand a lot of what this equation is doing before. Okay. Now it's kind of let's see kind of what changes when we go from an inequality constraint to an equality constraint. So a lot of our Rosenbrock function should stay the same. Our constraints are going to change a little bit because we need it to be better, or we need to better define what our actual inequality is. So we're going to square our x variable and our second set variable. So as we So now we need to kind of help define some more variables. So now we have this x2. So now we need to look at the second iteration. This is all from our understanding of our inequalities in general. So instead of just running the normal gradient value, we're also going to change this to a Jacobian. So we're differentiating the Rosen function, and we'll be using it or doing it at 3, or we did 3 instead of 2. So we're going to increase the iteration, but we don't want gradients, we want Jacobians. So now that we have all of our stuff together, so we want, put everything together, 1D constraints, we have our okay, Rosenbrock function, and here we go. Let's see, or concatenate. It must be missing something. It's always fun when your code runs wrong. So, I'm missing something. What do I not get? So we have our return function for the Rosenbrock. Looking at my notes from how I ran this code before, and it looks like we're missing something. So I'm gonna put it on pause while I get this figured out. All right, so I found my error in my return or define of this constraint. We're still multiplying the initial value by 2, when in reality we just want it squared. So now I haven't reran the function yet, so let's rerun it, see what we get. And against my notes from earlier, we're 100% right. So let's kind of, or for our inequality constraint, let's use the combination of our Lagrange multipliers as well as our slack variables to define a new Lagrange multiplier, and we're going to figure out and understand and kind of understand and be able to, or be capable to use all of these these high-level concepts to solve inequality constraints on functions like the 2D Rosenbrock function, which is one of the main ways that minimization is done. So now we're going to use a lot of the same stuff that we did before, except, okay, so we need our DL, which equals jax.jit, and we're going to do the jax.gradient of L. Whoop. Need to use a defined variable here. Okay. Now that we've defined DL, let's define x naught, which equals the same JMP array before that we're using here. So 0, 0.1, 0.1, 10, 1. JMP array. Now that we've defined our x naught, let's continue to define xf. We're using the same prints as before, so we can kind of better define what we're doing here. Woohoo! Did not want all of that. Control-C. Control-V. There we go, and let's run it. Woo! Got the same answers, so that means our Lagrange multipliers and slack variables, when applied, actually worked against our original defining Rosenbrock function and solving it the long way. So now that we've kind of culminated all of our knowledge on using the Broyden method, so the Broyden method up here, and it's a little hard to see, but our This is our combination of the Broyden method, our inequality constraint that we used, using all of this and its definitions to get to our function that we have now, and being able to solve the inequality constraint, which wasn't quite possible when we first were putting it into code. So as the rubber meets the road and we understand this really, I guess, verbose way to say all of our Rosenbrock or 2D function and creating the best ways to minimize, we've been able to do it, and that's what we've culminated here. And please, if you didn't understand anything, or if there's some stuff that was unclear that I mentioned I had talked about in earlier videos, please check those out. They'll be posted along with this one in the same playlist. So please check them out, and thanks.